The next part of our lesson considers more of a quantitative approach to our chemical formulas. We're going to begin this journey by talking about formula mass, sometimes called molar mass. Formula mass, might the name imply, if I look at a formula of a compound and I wanted to know its mass number measured in grams. The mass of an individual molecule or an individual formula unit, sometimes we hear it called molecular mass or molecular weight. This text tends to call it formula mass. Thinking about the sum of the individual atoms gives us something that's called like an atomic mass unit. But when I take a whole bunch of these called a mole unit, we can weigh out large quantities and measure with grams. The sum of the masses of all of the atoms in the single molecule or the single formula unit added together give us the entire weight of our compound. The sum of each of the parts will give us the whole, and these are quite easy to do. Using our periodic table, we find the mass of each of the elements, how many there are in our formula, and simply add the weights together. What would be the mass of one molecule of water? Well, notice there's two elements in water. On the periodic table, do you see hydrogen? It's the first element. On our periodic table, 1.008 is its atomic mass. Rounded to 2 decimal places, as this text will do, it will have us carry 2 decimal places for each of the weights. 1.01 atomic mass units, the weight of hydrogen. But see how there's 2 H's in water? So we're going to double the weights of the hydrogen. On our periodic table, find oxygen, and its atomic weight, 16.00. Since there's just one oxygen, we add all together 2 times the weight of hydrogen plus 1 times the weight of an oxygen, and we come up with 18.02 atomic mass units. However many elements there are in a formula, simply adding the weights of each individual atom to find the sum of the entire compound. Now, a single molecule has a weight of an atomic mass unit, but we can generally take the compound in terms of mole numbers. The relative masses of molecules can be calculated from the atomic masses of our periodic table. We just said that a molecule of water is found by adding 2 H's to the weight of an O, called its formula mass. But a whole mole of water still contains 2 moles of H's and 1 mole of O. Its molar mass would weigh 18.02 grams. Remember that large number called Avogadro's number, 6.02 times 10 to the 23rd. Anything's equal a mole. Well, if we had a whole mole of water molecules, it would weigh 18.02 grams. The molar mass of water, the amount of water per mole of compound. So very simple. A single molecule has a unit AMU, atomic mass unit, a single molecule. A whole mole worth of molecule, that's a lot of molecules, 6.02 times 10 to the 23rd, now has a weight of 18.02 grams. The term molar mass, how much would you weigh out to get 1 whole mole of a molecule, or a formula unit if it's a salt? Let's practice converting between moles and mass. Now, friends, part of your test-taking tools, part of the click on your Blackboard site where it said periodic table and other tool pages was a mole map. If you have your mole map out, boy, that would be helpful. If you're a visual learner like me, we can see the journey going from the scale in the bottom left into the center of the mole map right in the middle. Standing in the middle of your mole map, I can look up and see a balloon for volume. I look down right and see individual particles called atoms, or I can look down left and see a scale, things measured in grams. In the heart of all good chemical calculations is that central unit known as the mole. When we convert between mass, measured in grams, and the unit mole, you'll see right on your mole map the term is molar mass. How much would you weigh out to get 1 mole of a compound? And that's just as easy as adding the formula weight. The weight's off the chart. Suppose we had 50 grams of lead-4 oxide. Did you see how sneaky I was in putting that Roman numeral in there, just as a little bit of review? Oxygen we know is a -2. 2 units of a -2 tell me that lead is a +4. The name of that compound, binary ionic, that's lead, Roman numeral 4, oxide. Just sneaking in a little practice. If I'm given 50 grams of lead-4 oxide and I'd like to convert that into a mole, follow these steps. Given the number of grams as 50 grams of lead-4 oxide, we want to find the moles of lead-4 oxide. Our conceptual plan, we have to turn grams into moles of our compound. Following the mole map, we can see that relationship relies on the term called molar mass. I often say formula weight. I think that might be a little more clear in what it is we're doing. Take the formula and add all the weights of the atoms that contribute to the entire compound. Our formula for lead-4 oxide shows 1 atom of lead at 209.20 atomic mass units, and oxygen at 16.00, but I see 2 of them. Add the weight of those 3 atoms together, 1 lead and 2 O's, and we find a formula weight of 239.2. We know that a whole mole of lead-4 oxide would weigh 239.2 grams. That's called its formula weight, or the term molar mass. And now it's just dimensional analysis. Always start by writing the number, the unit, the label of what's given. 50 grams of PbO2 is the given amount. Next, we set up a conversion factor, a want over given ratio. We want the number of moles from the mass. Notice that by placing 1 mole on top, 239.20 grams on bottom, we get that gram unit to cancel. On your calculator, you would hit 50 times 1 divide by 239.2, or simply 50 divide by 239.2. When you do, your calculator screen will read 0.20903 moles. Changing grams into moles, we simply divide by the formula weight. Rounding to 3 significant digits, and we come up with 0.209 moles of PbO2. Knowing that grams cancel and we've converted into a mole unit. That's all we want to do, is to think about canceling units. What do we want from the given? Does your answer make sense? If 1 mole weighs 239.2 grams, and we have 50 grams, that's far less than a mole, so it makes sense that our number comes out smaller than 1. Let's work to find the number of carbon dioxide molecules in 10.8 grams of dry ice. That's the solid form. So, do you have your mole map? We're at the scale, 10.8 grams. That's a mass unit. We weigh things out at the scale. We want to know the number of molecules. Now the number of molecules is to the right side of our mole map, down on the right, far bottom right. I don't see a direct road between mass and molecules, but I do see a pathway to go from grams up into the mole and then down to the number of particles. A 2-step, 2 roads on the road map, a 2-step problem can convert grams into molecules. We must pass through the mole unit to do that. If our given is the mass of carbon dioxide, and we want to find the molecules of carbon dioxide, we must pass through the mole. Our conceptual plan would show grams of CO2 converting to moles of CO2. And literally, if I trace the road from mass into the mole, I trip over the conversion factor. It says we use molar mass. And if I follow the line then down for carbon dioxide into molecules, I literally trip over that conversion. We hit Avogadro's number, 6.02 times 10 to the 23rd. The molar mass of CO2, well, that's as easy as finding 1 carbon at 12.00 units, 2 oxygens at 16.00 units. 12 plus 32 is where we're getting the 44 grams for the molar mass of carbon dioxide. Grams divide by formula weight, multiply by Avogadro, and we've set up a 2-step mole map conversion. So always start by writing the number, unit, and label of what's given. 10.8 grams of carbon dioxide. We set up a conversion where we cancel the gram unit and head into the mole. When we cancel the gram, we divide by the molar mass of 44. Now, to head out of the mole, we multiply by Avogadro, 6.02 E23. Your scientific notation button is the E. Usually sits second function comma if you have a scientific calculator, TI-83 or something similar. Do not hit times 1023 or you'll be off a decimal every time. The calculator automatically does the times 10 when you hit second function comma EE. Now I know your calculator screen has EE, but when you hit the button, it only has one E show up. So when I say 6.02 E23, I'm reading your screen. There's no times 10, it's just 6.02 E23 to type in Avogadro's number. Try it out. Make sure your calculator key sequence is working. 10.8 divided by 44.01 times 6.022 E23 equals. Your screen should say 1.48 E23, and that's written as 1.48 times 10 to the 23rd molecules of carbon dioxide. Step 1, we canceled grams. Step 2, we canceled moles. And we've converted from mass into the number of molecules, a 2-step mole map problem. How many formula units are in 50 grams of lead-4 oxide? Now notice before we counted molecules in the previous example. That's because our compound were nonmetals hooked together. This is the same story problem, but we're counting formula units because now our building block is metal to nonmetals. It doesn't change a thing about the math, it's just using the correct vocabulary word to describe the compound that we're counting. If we're given 50 grams of lead-4 oxide, PbO2, we want to find how many individual particles there are, those basic building blocks of this compound that are called formula units. We need to start at the scale, head into the mole, and back out using the world of Avogadro. If we are given grams of PbO2, we'll need the molar mass, I sometimes say formula weight, to go from the scale into the mole. From the mass into the mole, we use formula weight. We had added that up a previous slide or two ago, 239.20 gram units. And we also know that 1 mole is equivalent to Avogadro's number. That number is anything that we're counting. We can count atoms, ions, molecules, or formula units, those basic pieces that matter is built of in the world of chemistry. Taking a gram and dividing by the molar mass and multiplying by the Avogadro's number will convert for us our mass into formula units. Start by writing your number, unit, and label of what's given. 50 grams PbO2. Our first conversion factor cancels the grams and brings us into the moles. We write that by saying 1 mole of PbO2 set over 239.2 grams of PbO2. Mole per gram. Where did we find 239.2? That's right, that's the sum of lead and 2 oxygens' weight off the periodic table. We then multiply Avogadro's number to find the number of formula units contained in 50 grams of our compound built of formula units. Key sequence, please double check your key sequence so we don't get off by a decimal and get our answers marked wrong. The key sequence would hit 50 divided by 239.2 times 6.022 E23 equals. Reminder, do not hit times or times 10 before you hit your EE button on your calculator. The calculator automatically says times 10 when you hit that, and if you hit it twice, you'll get off by a decimal. Does your answer give or make sense? Because that given amount is less than 1 mole, the number makes sense. We have less than a mole, so we'd have less than Avogadro's number's worth of formula units. How about the opposite direction? What if we're given the number of molecules? I want to know how heavy they are. Converting molecules into mass. Well, friends, it's the same 2 steps, but in the reverse order. Given the number of molecules, now again, notice the correct vocabulary, NO2, 2 nonmetals. This is a binary molecular compound. Nonmetals combine. The name, with molecules, we hear prefixes. Nitrogen dioxide, a binary molecular compound. We have a large number of molecules and want to know how heavy that would be. Given the number of molecules, let's find the mass. This time on our mole map, we're starting on the far right side. We've got to go up into the mole and then back down to the scale where we measure in grams. So our conceptual plan says we have to pass through the mole. There's no direct road between the world of counting and weighing. Start with the number of molecules, converting that into a mole, and converting that back into a mass. So molecules to moles to mass. We're going to need a formula weight, or the term molar mass. We've got to add an N and a couple of O's together. Find N on the periodic table. Its weight, 14.01. Oxygen's weight on the periodic table, 16.00. There's 2 of those, so we'll need to double it. The formula weight, or the term molar mass, 46.01. The other relationship is a standard. We know Avogadro's number will be used to convert when counting. So if our solution says we've got to cancel molecules first and then head out to the scale, step 1 divide, step 2 multiply, a 2-step mole map problem. This time we divide first by Avogadro, then we multiply by the molar mass. In our first conversion factor, we need the term molecules to cancel. And then in the second step, we need moles to cancel. With this key sequence, we would hit 4.78 E24. Are you hitting with me? 4.78 E24. Grab your calculator. Divide by 6.022 E23 times 46.01. And I hope you hit and found 365 grams of NO2. Step 1, divide by Avogadro to go into the mole. Step 2, multiply by molar mass to head out of the mole. Let's stop here. Start upping again when we're ready. I just have to grab my calculator.